Okay, welcome everybody to today's CDAC webinar. It's a pleasure to introduce today's speaker, Nick Butch, who holds positions at the NIST Center for Neutron Research and the Quantum Materials Center at the University of Maryland. Nick is an experimental condensed matter physicist with a special expertise in superconductivity, strongly correlated materials, and other quantum materials, including the behavior of these materials at extreme conditions, such as high pressures, very low temperatures, and also very high magnetic fields, which he'll tell us about today. Nick has a bachelor's in physics and ceramic and materials engineering from Rutgers, a master's and PhD from UC San Diego, where he worked with Brian Maple, and he was a postdoc at Livermore with Jason Jeffries, and also at the University of Maryland, before joining NIST as a physicist and faculty at Maryland in 2013. So over to you, Nick. Thanks for agreeing to give this talk.
Thanks for the introduction, Russ, and thank you for the invitation to talk about, I guess I would say by now, my favorite material, uranium ditelluride. I hope to share some of the excitement with you, and there's an awful lot going on in the study of this material. So I hope that everybody gets a little piece of the enjoyment and excitement. In particular, this talk is about the phase diagram, shall we say, of the material. I'm going to cover a bit more, but since we like to talk about extreme conditions, this will be high fields and maybe not the highest pressures you usually deal with, but let's call them moderate. So before I get started, I want to acknowledge just the people who have contributed to this project, or projects at this point. Sheng Ran was a postdoc at NIST and also worked at the University of Maryland. He is he was there at the discovery of superconductivity in uranium ditelluride. Now he's faculty at WashU in St. Louis. This is my current group, postdocs and grad student. We have a very strong collaboration with the Paglione group at the Quantum Materials Center, and others like Steve Onlaga, Shanta Saha, Ian Hayes is one of Paglione's postdocs, and Shiro Takeuchi's. And of course, with many, many other people who I may not be calling out by name, but we'll be highlighting some of their work during this talk. And I should say, I only have an hour, so I apologize if anybody's watching and feels slighted that I didn't include them. It's not because I don't like you, it's just that we have limited time, and I'm going to focus on the stuff that the UMD collaboration has particularly been involved in. Also, if there's anybody listening who is looking for future postdoctoral fellowships, this one's open to US citizens. We have an NRC postdoc program at NIST that I invite you to contact me about. Okay, so this talk is going to look, it's pretty simple structure. We'll start with the basic properties of uranium ditelluride. Then we'll talk about the superconducting order parameter, which is arguably why most people care about this material. We do believe that it's a spin triplet, and I'll cover some of the controversy and sort of the most recent happenings. And then at the meat of the talk is going to be talking about the different phases, in particular multiple superconducting phases, both at high pressure and at how they evolve as a function of applied pressure. I'm sorry, did I say high pressure? High field, and then pressure. All right, so to start with, the first measurements, shall we say, that convinced us that UTE2 is a superconductor and not basically a paramagnetic heavy fermion boring compound are shown here. So actually the material, or at least we knew about this stuff for now 5 years. It took a while to get published, shall we say. But yeah, earliest samples that we had showed a superconducting transition around 1.65 Kelvin. You can see that in the resistivity, the magnetic susceptibility, and in the heat capacity. And in the early days, I'll point out that it looked like maybe, so that first of all, in the normal state, this is a pretty large heat capacity, which implies a big Sommerfeld coefficient. And in the early days, those samples only showed that about half of that was getting gapped out. That has since evolved. Okay, but if we want to talk about the, as I said, maybe boring material, although it's really not boring, but the non-mag not non-ordered, so not magnetically ordered metal from which superconductivity emerges, we need to take a look at the electrical resistivity and the magnetic susceptibility. Again, these are typically the first things one measures when it has like standard equipment in the lab. And this is an orthorhombic system, and so it's pretty clear that the electrical resistivity is anisotropic, as is the magnetic susceptibility. So the other thing is that if you're used to just looking at simple metals, you'll note that the slope here is wrong. The resistivity actually rises. It's not because it's a semi-metal or a non-metal. This is because of Kondo lattice physics, as we'll talk about. And the magnetic susceptibility, in particular this green curve, the b-axis, has a local maximum. Again, a signature of coherence. And this Wilson ratio, which is the ratio of the susceptibility, the heat capacity, I'll just say is sort of typical. It's not like some kind of big outlier. So if you didn't know about the superconductivity, you would think that this was boring. A heavy fermion compound, but nothing to get excited about. So as I mentioned, it's not magnetic. And in fact, people have been looking for signs of magnetic order now for 5 years. Neutron diffraction studies were done in 2020 or published in 2020 and down to 2.7 Kelvin. And let's just say from other measurements since then, it doesn't look like there's any sign of actually long range magnetic order. This is still a topic of discussion. Okay, what about the electronic structure? Well, we know actually quite a bit about it, but I want to start kind of walk you through this. So on the left side, I have this called F-less Fermi surface. And so this is an LDA calculation for the hypothetical thorium-tellurium 2, which doesn't exist, but let's say bypasses the typical issue with calculating what's going on with F electrons by just ignoring them. And in that scenario, you have these 2D-like bands. Basically, this is just a Fermi surface that comes from two kind of 1D bands crossing, anti-crossing. Okay. Now, when photo emission studies were done, this general structure was confirmed with an additional signature of a three-dimensional pocket that's small. It looks to live maybe up here. And the actual details of it are still not completely settled. Much more recently, so within the last year and a half, we have finally gotten data from quantum oscillations. And so they confirm this, again, roughly two-dimensional shape. The masses that are inferred from the oscillations are heavy. So again, I said this is a heavy fermion compound, so that all makes sense. And in addition, more recently, even signatures of that small pocket have been seen in quantum oscillations. And so what the electronic structure of this looks like is got these kind of general 2D like sheets and then a small 3D pocket. And I'll just back up real quick because I don't think I showed again. But just again, one of the sort of things that people are thinking about is how does something that looks like it's mostly a two-dimensional Fermi surface give you a somewhat isotropic 3D electrical resistivity? So that's an open question right now. It seems to be, you know, people like to say or think perhaps that small pocket is the thing that's responsible for the isotropy. Okay, now the real excitement that we felt when we were first studying superconductivity in this material was not just that it's a 1.6 Kelvin superconductor, because there are a lot of 1.6 Kelvin superconductors that don't do anything interesting. It's the field dependence that immediately jumps out at you, that is something weird going on. And that's what we're showing here. And so the first thing to note is, so again, 3 different directions, B, C, and A, those are crystallographic axes. And in all directions, even in these early samples, the upper critical field at 0 Tesla, I'm sorry, at 0 temperature, is larger than the, let's say, the typical estimate of the Pauli paramagnetic limit, which would be 3 Tesla for this TC. But the most obnoxious thing, or let's say unexpected thing, is that if you apply field along the b-axis, at some point, the transition just doesn't go down. And since JP has a 20 Tesla magnet at UMD, we were able to study this up to 20. And we immediately could tell that this was, you know, really, really strange. And the first thing, of course, you do is you check to see whether your magnet's actually operating, because this doesn't happen frequently or ever. And after checking it a bit, we were, we were convinced that this is real. Okay, it turns out, as I've sort of shown in the dotted line, and we'll talk about a lot more, that this superconductivity extends up to 35 Tesla. So what happens at 35 Tesla? Well, here we're showing you a resistance plot with field along the B axis. And this is taken in Tallahassee at the DC Field Lab. Basically, the resistance becomes non-zero slightly below 35. This is coincident with a jump in the magnetization that occurs at the same field. So this is what we're calling a metamagnetic transition. So this is a first order magnetic transition. And so a thing to just keep in mind is this actually implies that the superconductivity wasn't orbitally limited, but was actually destroyed by a change in the underlying electronic structure, which is a different thing altogether. And so in the absence of this metamagnetic transition, it could actually, in principle, go higher. And we'll see signs of this actually from our pressure experiments. So please keep that in mind, especially if I forget to say that later on. So what about this this transition? So it's actually, it extends up quite high in temperature. I'm sorry, certainly higher than the superconductivity. So you can track the anomaly associated with up to about 20 Kelvin. It seems to be a critical endpoint about 10-ish, where it stops being first order. And there are other things that happen along with it. And so there is this understanding that potentially that the electronic mass is changing and diverging. I mean, in the sense that, maybe going up by a factor of 2 at this transition. So that implies that there is a change in the electronic structure that's going along for the right. Okay, well, what about just pure numbers and excitement? What I'm showing you here is the angle dependence. So in essentially the zero temperature limit, the field angle dependence. So this is the field strength and then field angle. B axis is the sort of exciting one. When you think about this superconductivity here that persists to 35 Tesla, above which we go into this field polarized phase. When we're looking at low field, the upper critical field curve can basically be described fairly well by an anisotropic effective mass model. And so it looks like it's a 3D, or it would be consistent with what you expect from a 3D superconductor. Of course, the big thing that sticks out here, or should stick out because I put a yellow arrow, is this SCFP phase, or superconducting phase inside the field polarized state. And we this has been dubbed by the MagLab press office the Lazarus phase, because it comes back to life. And we kind of stick with it, I guess, for brevity, but it's also cute. So what about this thing? So we can also look at the temperature dependence of this Lazarus phase shown here and compared to the low field superconductivity. And the TC seems comparable. And actually, this is an active field of study. So I'm not going to really get into the models that could be applicable here, but just to suffice it to say, there isn't a whole lot out there that really well explains having stable superconductivity with this low TC at this high field. And if we want to put things into real perspective here, on the right, we show the HC2 curves of, let's say, a whole bunch of families of superconductors. Your BCS superconductors, your iron pnictides, and your cuprates. And you'll of course note the trend that the higher the TC, the bigger the upper critical field at zero temperature, right? But when you plot the HC2 versus T of UT2 on this plot, this is basically a delta function, okay? It's quite unusual. And it really shows how the ratio of TC to upper critical field here is really, I would say, unique. Okay. And more recently, so we've been studying this. We're trying to understand again what about the stability and potentially what can we say about physical mechanisms that would be responsible for just making this phase possible. And one of the more interesting, actually, it's a very exciting find that we posted fairly recently, is that with disorder, and that shouldn't be a surprise to this audience, that with disorder, that superconductivity can be suppressed. What is surprising is that we can preferentially suppress the low field superconductivity while maintaining the high field superconducting phase. And you might say, so what? Well, typically, when we're talking theoretically about models that talk about stability of high field superconductivity, they assume that there is low field superconductivity already in place and sort of figure out ways that field doesn't suppress superconductivity or the field enhances superconductivity compared to zero field value. So it's really quite remarkable that we have an experimental example of high field superconductivity, not at 20 Tesla, at 40 Tesla in material where there is no zero field superconductivity. So the question remains, and this is an active field of study, why is it so robust? Okay, and now I want to sort of start making a connection. This is what I have said is a unique and weird compound to things that we already know about. And the most obvious relatives or potential relatives, because we don't really know for sure how strong this relationship is, are the uranium-based ferromagnetic superconductors, uranium, rhodium, germanium, and uranium, cobalt, germanium. The big difference is both of these are actually ferromagnetically ordered before they're superconducting. And in both cases, the rhodium and cobalt case, there is also reentrant superconductivity, albeit at slightly reduced field scales. You'll also note that the superconducting transition temperatures are lower. And that's okay. But this was the first thing that jumped out at us was, well, hey, maybe this is similar. Okay. Now, what else do they have in common? Well, structurally, there are uranium chains in these compounds, and so there seems to maybe be a shared motif. Again, keeping in mind that UT2 is non-magnetic. There's also a similarity uranium-germanium 2, which happens to not be superconducting until you put it under pressure. Okay, as I already said, neutron diffraction shows nothing going on magnetically in terms of long-range order. But at the end of the day, and the reason I went through this was to sort of motivate this cartoon phase diagram where we plot or where we compare UT2, uranium, cobalt, germanium, uranium, rhodium, germanium, and uranium, germanium 2. Remember, this one is not a superconductor at ambient pressure. These two are, and TC here is, so this is sort of Curie temperature and superconducting TC. The idea here would be that uranium ditelluride might be the end member of a series of ferromagnetic superconductors. The end member in this case not actually undergoing magnetic order, but in some anthropomorphic way wanting to or being on the verge of it. And this is interesting because ferromagnetic triplet superconductors usually have an equal spin pairing state, and that state generically supports topological superconductivity. And so now we start talking about whether UT2 might also be a topological superconductor. All right. Now, even though there isn't ferromagnetic order, there are signs that there are ferromagnetic correlations. So, you know, it's just on the border. This is coming from muon spin relaxation. And so this story has actually evolved to the point from USR where the data are interpreted as suggesting that there's actually short range order and short range ferromagnetic, I think it's ferromagnetic order in some kind of clusters, which haven't been actually detected otherwise, but that's what MUSR is saying. So it evolved from looking at a response that looks like potentially quantum critical like to one where there's actually some kind of frozen short range order. And not similarly, but a complementary experiment that suggests that the material is strongly magnetically polarizable is optical co-rotation in the normal state, not in the superconducting state, which, you know, again, says the electrons are almost there. Okay. How about neutron scattering? There have been several studies actually done, including from our group, that first of all, pointed out that the obvious and strong inelastic scattering occurs at incommensurate momentum transfers. And so that's not consistent with a ferromagnetic description at all. And rather, we should all be worried about antiferromagnetic spin fluctuations being the dominant spin fluctuation in the material. Now, I want to point out before I get into a short discussion of our research on this, that even with these putative antiferromagnetic spin fluctuations, there is no antiferromagnetic order. And if you note here, let's say from energy, and this is just intensity, this is just the plots at a certain momentum transfer, the peak at of these fluctuations is somewhere around 4 MeV. And an MeV is about 10 Kelvin. And so for a 2 Kelvin or below superconductor, this is a very high energy scale. And we'll get into the shape of this a little bit in the next slide. So we performed neutron scattering experiments at NIST on this material. We did it in an AB plane, just for those who are keeping track. And what I'm showing you here in this plot are, we call them constant energy slices. This is integrated from 1 to 2 MeV, 2 to 3 MeV, 3 to 4 MeV, 4 to 5 MeV, okay? And overlaid is this red pattern. This is the reciprocal space. This is Brillouin zone of this material. The zone center is blue, and the top of the zone is red. Because this is a body-centered configuration, actually, when you're going in this plane, you're switching between, the neighbors are, this is the top or bottom of the neighboring cell. So that sort of explains it. Or you could say we should need to go on a diagonal. At any rate, the strong excitations exist and are constrained or confined to the zone, the Brillouin zone edges, and only along the B direction here. And they're incommensurate because of this. So they don't happen at some kind of small integer fraction. They happen precisely at the Brillouin zone edge. And that's where this incommensurability comes from. But it's not a feature of the Fermi surface or some other thing that might not share the periodicity of the crystal structure. It actually comes from the periodicity of the crystal structure. Okay, now if we take a look at the energy dependence, let's say along this green line, we see this V-shaped dispersion. So that's basically, that's the energy dependence, energy momentum dependence of these excitations. There's a V shape along B, and in the perpendicular direction, it's rather energy independent. So we can draw something like this. This is not the kind of response that you would expect from paramagnetic excitations. In fact, generically, paramagnetic excitations should not be long-lived in this sense. They shouldn't actually be they shouldn't occur at finite energy transfer. They shouldn't peak at a non-zero energy. They should be quasi-elastic. So they should be much lower in energy, and they should be centered on the elastic line. So if we integrate the intensity, and just for, let's say, the simplicity of plotting this, look at the temperature dependence of these excitations. We'll see that at low temperature, so even in the superconducting state, they're always peaked around here, around 4 MeV, and the intensity simply dies down as you heat up the sample. Now, what's special about, oh, and I should also mention again, so we're talking again about the similar energy scale or temperature scale of 20 to 40 Kelvin, if you recall from the magnetic susceptibility when there was a maximum in the B-axis susceptibility. This number 4 MeV, as I said, 1 MeV is roughly 10 Kelvin for KBT. This is consistent with the hybridization gap that was measured in scanning tunneling microscopy. And the 40 Kelvin temperature scale is also consistent with the development of a sharp Drude peak below 40K in the optical conductivity. Again, going back to this Kondo lattice picture where a heavy fermion state is developing below 40K with this 4 MeV energy scale. And so that's the picture. That's what those excitations are. They're probably not related to antiferromagnetic interactions, let's say between local moments or even itinerant moments like we would like to talk about, but rather they are a sign of scattering of a Kondo lattice developing a coherent electronic state. And I didn't just pull this out of thin air. There's actually been work that's fairly old at this point that predicts similar behavior. It's not often observed or talked about, but that's my understanding right now of those dominant responses in neutron scattering. Okay, so let's talk about the superconductivity. So why do I confidently call this a spin triplet superconductor? Well, we can say there's a lot of circumstantial evidence because you can't just use one measurement to make that argument. But we started with saying that the upper critical fields are bigger substantially than the Pauli paramagnetic limit. Nuclear magnetic resonance night shift measurements all suggest that or because there's a very small change or negligible change through TC, that this is not spin it's not a fully gapped superconductor, or at least there are nodes in the system, which would be consistent with the triplet state. There are more recent NMR measurements that suggest that in quote unquote higher quality samples that there's actually substantial night shift. I'm going to say the story is, or rather, that case is still open. But to date, the published data suggests still that this is spin triplet from NMR. Okay. Now there are other arguments that the superconducting the gap structure is nodal, including heat capacity, penetration depth. This is coming from microwave measurements, and thermal conductivity. None of them are consistent, with the exception of some recent work where they're claiming that they've got an isotropic gap. But so far, I would say the evidence that we have, and there would be more forthcoming, is consistent with there being point nodes in the system, like you might have in a p-wave superconductor, and that would be a spin triplet state. Okay. All right. So there is some controversy, but I also wanted to highlight before we start talking about that the recent reports of the detection of a paired density wave. And this is coming from, again, scanning tunneling microscopy experiments that I'm showing here from the Madhavan group in Urbana and Davis group. And so what they see is evidence for charge density wave state in the normal state. So charge density wave that's shown here. This is the Fourier transform. Pair density wave, which is basically spatial variation of superconductivity in the superconducting state, and that these two things are related. And so the supposition now is that a pair density wave might be responsible for all of this superconductivity. I'm going to leave it at that. So if it's true, this would be a really exciting development, kind of add it to the list of superlatives in this compound. Okay. But what about the topology? And this is a fairly, I'm going to call it kindergarten type approach to topological superconductivity, and saying I have a checklist and I want to convince you, or at least show evidence that we have satisfied all of these things. So to have a topological superconductor, a nodal spin triplet superconductor, we want to see evidence of chiral surface states that would be these Majorana modes, zero energy. We want to see evidence of time reversal symmetry breaking, or equivalently the presence of a spontaneous moment in the superconducting state. And that actually requires that there's a two-component complex order parameter. Or at least I don't know of a way to have that without having a two-component order parameter. And so actually this was shown in the first STM study published, again, from Madhavan's group, that there are surface states and they're chiral. So there's the actual shape of the spectrum is not quite understood, but the chirality comes about from the fact that there are these kind of linear steps on the cleaved surface of the material, and they have, let's say, orange and blue direction. So either up or down, however you want to define it. When you're on the orange part, they always look one way, and when they're on the blue part, they always look the opposite. And so just, again, that's the definition of chirality, that there's a handedness to it. The evidence for time reversal symmetry comes from the optical Kerr effect. This is from Kapitolnik's group. And then there were and continue to be in many samples signatures of a double transition in the heat capacity. That is, two transitions. Now, this last thing has been quite controversial over the last, let's say, 2-3 years. And so there are arguments that those two transitions are not intrinsic, that rather they're coming about because of defective samples or not high quality samples. And the first thing to note is that even from the earliest days, we knew that not all samples were superconducting, because we weren't the first ones to make UT2. And we know that it was before possible to make non-superconducting material. So in principle, you have the ability to somehow tune the superconductivity. Now, as time has gone on, the idea has emerged that there's only one transition in quote unquote higher quality or higher TC samples. Now, that's not quite true, but it tends to be true as 2 Kelvin is approached in terms of TC. The transitions get sharper, and also the low temperature heat capacity has a tendency to get smaller, although this actually is also not quite properly understood. And then furthermore, people have, or some groups have gone to the lengths of cutting their samples and showing that the amplitude of the height of the jump in the heat capacity varies in the different pieces. And so the argument there is that this is actually a symptom of heterogeneous superconductivity. On the other hand, I have only one thing that still stands out to me is we really in everything published really only ever see at most 2 transitions in the heat capacity. So it's interesting that when there is some kind of splitting, it typically leads to a bifurcation, not to sort of a broad distribution of TCs. Now, more recently, additional arguments in favor of a single order parameter have emerged. One of them is that under uniaxial stress, there is no splitting, in particular in the 110 direction, which is the in-plane diagonal. Even if the a 2-component order parameter were accidentally degenerate, there would be some expectation that the 2 transitions should shift differently, and there'd be a splitting there. And that wasn't seen. It's not a definitive argument, because I guess there's always a way out, but that was suggestive. And more recently, ultrasound experiments show that there are only weak anomalies through TC in the shear modes, as opposed to compression. Again, the argument there is that a 2-component order parameter would couple to the shear modes, and so if it were 2-component, you should see something stronger. And this calls into question now, so if it's not a 2-component order parameter, what is responsible for the optical curve rotation? Why does it look like there's time reversal symmetry breaking? And that's an open question. So that also leads to suggestions, well, maybe there's magnetic junk on the surface, etc. So we're still back to arguing about whether the quality of the samples is sufficient. Now, in some sense, theoretically, I won't say it doesn't matter, but the cases have already been considered. And so what we're showing here, so there are only the irreducible representations are all called singly degenerate. I'm losing my language here, but the combinations of them, like B3U plus IB2U, would be I guess accidentally degenerate combinations, but theoretically, basically a lot of these different combinations have been proposed, and so bases have been covered. Okay, now there is a caveat, and this is an experimental one, and it's one that I think still bothers me, and it's something that I think is still worth exploring in more detail. Now, it turns out that even though it looks like there's only a single order parameter, a single superconducting transition equivalently at ambient pressure, it doesn't take much pressure to actually induce 2 transitions. And so if you're looking at these phase diagrams, even starting here, you got an SC1 phase and then an SC2 phase. And it looks like, and this is from calorimetry, that something here, question mark, what's happening? How does this evolve from here? This is a pretty low pressure, right? It's about 0.3 GPa or 3 kilobars. So interestingly, even in the Los Alamos work, they actually they amended their paper to show that there isn't actually there aren't 2 transitions sort of in the 0 pressure limit. This seems to be the consensus view, other than the fact that there are implied, or that people are still thinking about whether this what's going on here. And so one of the arguments that has been offered since the beginning in terms of the symmetry of the material is that an orthorhombic crystal structure with spin orbit coupling should only be able to support a 1-component order parameter. And now clearly, as a function of pressure, that is violated because it's still orthorhombic, but yet there are clearly 2 superconducting transitions. So how this relates to the 0 or the ambient pressure superconductivity is an open question. And so how this superconductivity either goes away or the signatures of it become undetectable is I think still an open question. Okay, but we're going to shove that under the rug and sort of move on to higher pressures. So before I start talking about high pressure, I'll just flash these phase diagrams at you again, the pressure dependence from, let's say, the early days showing, and let's just focus on what's going on here. So, and this is with no field. We'll notice again, as I said, there's two superconducting phases. One of the other things to note, of course, is that the superconducting transition temperature increases. And now in all these data sets, there is a critical pressure of about 1.5 GPa, somewhere in that neighborhood, okay, where the superconductivity goes away. And then on the other side, there's some kind of long-range magnetic order whose nature has not actually been definitively established yet. Okay, but 1.5 GPa is kind of this magic critical pressure. Now, before I move on, I wanted to acknowledge that the material has actually been studied to even higher pressures. Now, some people in this community might still scoff. 10 GPa is not that high, but it does undergo a structural phase transition at around 6 GPa. And in fact, in the higher pressure phase, it's a superconductor again. The interesting thing is that the upper critical field of that superconductivity is not all that dramatic. And so it seems like all of the interesting stuff, not the nicest thing to say, I guess, but we're focusing our attention, shall we say, on the much lower pressure range. And that's what I'm going to be talking about for the rest of the talk. All right, so just to remind you again, this is the sort of effective zero temperature phase diagram with field along the vertical axis and field angle on the horizontal axis. And so remember that A, B, and C are the high symmetry crystal directions. And then there's this special kind of range of angles here where this so-called Lazarus phase exists. Here is a summary of the pressure dependence. So, and pressure versus field here, again, effectively at zero temperature for these four directions. And so I think the easiest thing to look at, well, we'll start and we'll look at these phase diagrams in slightly more detail, is along the A axis and the C axis, where we'll see the superconductivity, the TC is going up, as I mentioned before, and then it makes way for this magnetic order. And it seems like the critical field of this magnetic phase is also direction dependent from the data that we have. And then we'll switch gears and we'll talk more about the measurements along the B axis, where this is this high, that 35 Tesla superconductivity exists, and then what's going on with the Lazarus phase. So first, I want to point out that it's not even just two superconducting phases potentially when fields along the A axis. Aoki and company actually suggests that there are, looks like 5 superconducting phases that evolve in a very interesting way. So these are field versus temperature phase diagrams at constant pressure as you pressurize this. And so this is kind of interesting pinching and these weird kind of shapes in the upper critical field curve. And so there might be quite a lot actually going on here. There isn't the same kind of point density as a function of pressure, at least published for the field along the C direction. Well, what's interesting in this case, or what I'm trying to point out here, are at these pressures on 1.45, 1.55 GPa. Remember, critical pressure is about 1.5, and there's always some uncertainty, shall we say, from experiment to experiment. But what looks like at high field above this magnetically ordered state, that there's a pocket of high field superconductivity. And actually, we also saw a similar thing, albeit at much lower fields here along an intermediate field direction in one of our early pressure studies. So superconductivity, and we don't know if this is full volume fraction or not, but this actually even seems to peak out above the critical pressure into the magnetic phase. All right. So what about the B axis and this Lazarus phase? Well, let's start with the B axis, and I want to walk you through this a little bit. So remember, I showed you a resistance curve. So resistance versus field with, this is a temperature 0.35 Kelvin. 0 degrees means it's along the B axis, and there's this jump at the metamagnetic transition. So it goes from 0 and just like that. As you slowly tilt the field away from the B axis, 5 degrees, 7 degrees, you'll notice that there's a jump now, instead something like 15 Tesla and then some weird shape, shall we say, and actually truly reentrant superconductivity in the sense that you got a superconductor, then not, then a superconductor again. Okay. So this is the ambient pressure. This is the ambient pressure situation. And then what happens as a function of pressure is that, as these arrows are showing, the metamagnetic transition is suppressed. 30 Tesla, 24 Tesla, so that's at 8.5 kilobar or 0.85 GPa. And around the critical pressure, this is where we're losing it. So you can still see it at 14 kilobar, but it's quite substantially lower. Very similar features, though, happening in the resistance. And these are as a function of temperature. So this is a giant jump. So it's a very easy feature to track. And so if we plot all those together, you'll see that this transition is suppressed. Okay. Now, it turns out that in diode oscillator experiments, there's a second lower field feature that also has a pressure dependence, and it's plotted here. And from this data, it was inferred that this is actually the phase boundary between superconductors. So you can't see that in electrical resistivity because both states are zero resistance states, but the diode oscillator experiments are essentially kind of a surface conductivity experiment or measurement, which could be sensitive to changes in something going on in the two different superconducting states. It is a subtle feature, though. Okay. Now, I mentioned before earlier that if it weren't for the metamagnetic transition, that this superconducting state along the B axis would be would have a much higher upper critical field. And what happens when you suppress the metamagnetic transition with pressure here, so 4, 8.5, and 14 kilobar, is that you see that the initial slope here so HC2 versus T here, or as a function of T, is really large, and it just looks like the metamagnetic transition, again, here in temperature, is cutting off this superconductivity. And it would extrapolate up to ridiculously high fields, such as 72 Tesla from this initial slope. Similar data were seen by Nebel and co-workers as well. Okay. So the takeaways here is that pressure decreases this metamagnetic transition, but it always acting as an upper bound for the superconductivity. And then magnetic order is on the other side. Okay. Now, what about the Lazarus phase? So this is now looking at this direction. I want to point out, actually, so this paper that I'm about to talk about was actually squeezed out, or the data were taken right before COVID shut the world down. These were done in the 45 Tesla hybrid magnet at Tallahassee. And what I'm showing you here looks like a bunch of rainbow colored stuff. But these are both diode oscillator and resistance experiments, same pressure cell, slightly different angles because of how the samples rotated. At 0.85 GPa, 1.12, and then as you approach the critical pressure. And remember that this metamagnetic transition here is the lower bound of the field polarized superconductivity, this Lazarus phase. But it's the upper bound of the low field, in this case, low field being like up to 30 Tesla superconductivity. And you can see clearly in both these cases how this line is kind of, I almost think about it like a squeegee or like a window shade coming down, exposing the higher field electronic state and kind of squishing down the low field electronic state. And that these two superconductors just happen to live on opposite sides of that fence. So you'll notice that under pressure, this Lazarus phase, which before looked like it was a triangle as a function of field, so the field temperature phase diagram looked like a triangle. Now when you cut the bottom out, it looks like a dome. And then, of course, this part down here, the low field part just gets squished and goes away, as we saw in the previous case. Another thing that happens, and this is sort of piqued our interest, is that a kind of anomaly shows up here in the diode oscillator experiments that has the same kind of a temperature dependence as one would see in quantum oscillations. It clearly doesn't satisfy isn't a good enough data set to call them quantum oscillations. But one of the reasons that we're interested in it is that the presence of Landau levels is one of the few possible mechanisms by which one can stabilize high field superconductivity. All right, so I have this slide here mostly to show off in B. So we can talk about all these little details. It's probably too much for this talk about how the first order nature and the second order nature of these phase transitions evolve as a function of pressure. But one really cool thing is to see an R equals 0 state. So here at 0.4 Kelvin, all the way up to 45 Tesla. Now you could say, what's going on here? This is because we typically don't go below 11 Tesla in these experiments, but you can be rest assured that this was also 0. So that's pretty cool just to show. All right, so to put these guys together, this is B axis, of course, and this is like an intermediate angle, 25 or 30 degrees. We'll say again, this metamagnetic transition, which at ambient pressure is up here, gets suppressed by pressure, but it always forms the upper bound of this lower field superconductivity, and it always forms, sorry, the upper bound here and the lower bound of this state. And so it seems pretty apparent that you actually have two different electronic states, as I have mentioned several times during this talk, that are separated by this transition, and that this magnetic order is, again, it's on the other side. And so in this case, it looks like pressure and field are tuning toward the same electronic state. And it's nice that both of these are actually experimentally accessible. So I just told you that this metamagnetic transition is being suppressed by pressure. It turns out that there's actually even more suggestive evidence. And so the first thing to say is what's happening, or talk about, is what's happening to the magnetization itself. And so here you've got field parallel to A and field parallel to B. And you'll notice that at this 35 Tesla transition, where there's a giant step here, the B axis magnetization actually overtakes the A axis magnetization, becomes bigger. All right. So hard to say that it's an easy axis. That's maybe not the right way to put it, but the B axis magnetization does become larger at this field. Similarly, under pressure, the easy axis switches. So between ambient pressure and 1.7 GPa, the magnetic easy axis, so the highest susceptibility, changes from being the A axis to the B axis. Again, the B axis takes over on the other side of either the metamagnetic transition or the critical pressure. Now, furthermore, NMR experiments have been done under pressure, and they also seem to be sensitive to this change, suggesting that, in this case, more specifically, the ground state changes from a Fermi liquid or heavy fermion configuration to this magnetic order above the critical pressure. So there's multiple pieces of evidence suggesting that the electronic structure is changing at 1.5 GPa in the same way that we believe that it's changing above 35 Tesla, so with field along B. So to conclude, I talked about uranium ditelluride, how it's a spin triplet nodal superconductor, and I discussed some of the ongoing research into identifying the wave function, talking about whether it preserves or breaks time reversal symmetry, and whether it has topological surface states. I also talked about the field and pressure phase diagrams. I'm going to say unprecedented here. It is complicated. There are numerous superconducting phases. Which of them are unique or not is a still open question. We're working on it. I hope I convinced you that the metamagnetic field and the critical pressure are one and the same, or they're the same phase boundary. And that's it. Thank you for your attention, and I'm happy to take any questions.
Thanks very much, Nick. What a wealth of phenomena. Okay, this talk is open for comments and questions. Just use the chat or unmute yourself, raise your hand. Okay, Danny Haskell.
Hi, thank you, Nick. That's a wonderful talk. Question about the per-density wave and CDW. In that picture, is there any competition between these two states? Is the modulation in the order parameter, the superconducting phase, driven by a desire to preserve CDW in some parts of the lattice, or it's not like that?
That's a great question. And so my understanding, let me let me preface it with that caveat. My understanding is that the pair density wave is in some sense the parent phase. So there is a an instability towards this state. The charge density wave is the thing that is observable in the normal state. And then when superconductivity appears, then that modulation, so the modulation comes from the pair density wave. If I remember,
Maybe we lost him.
Oh,
He seems frozen.
Nick, are you there?
Sorry, I didn't want to cause any trouble.
Well, he's left the meeting. Okay, well, I've sent him a message. Well, I'll stay on for a few minutes, see if he rejoins. Okay, well, he's not returned. I was going to ask if there was any structural similarity between the Lazarus phase and the phase you reach 100 or 1.5 GPa. I wonder if anybody has any comments on that. If there's a crystallographic parallel between the two phases. Okay, well, this is unfortunate. It was a great talk.
Yeah.
And it's recorded, so you can go back and watch it. We'll have it posted probably by the end of the day. So thanks for joining us.
Bye.